In this video we're going to discuss a concept called differentials. This goes along with linear approximation. So we're going to have this formula for our differential, and I'm going to use this picture down here to explain what we are looking at. So we have a function f of x that's going to be this blue curve, okay, y equals f of x. This pink line is our tangent line at a, so that's like our linear approximation of this function. Okay. So the idea is for our actual function, if I want to go from an x value here, say at a, to another x value on my graph, which would be here, that difference is what we would call delta x, right? It's my change in x. So from here to here, that's going to be a difference of delta x. So this x coordinate would be a distance of x plus delta x. Okay. My difference in y value, it would be delta y, right? So I have my y value here, I have my y value here. That difference is called delta y. So change in x going from this point to this point, and then change in y, delta y, going from this y value to this y value. Now with your linear approximation function here, we don't call the change in x delta x, we call it dx. Okay? So dx is going to be the same as delta x. That doesn't change, right? That's the same distance. So from this x to this x, we're calling that that change in x, we're calling that dx. But instead of delta y giving me my difference in y value, we're looking at something called dy. Okay, so dy is the derivative function times that change in x. Okay, so an important note: dy is not the same thing as delta y, but the idea is if I make delta x really small, which means if I make the difference in my x values get really small, so those two x values are getting really close together, then I think that you can see that dy and delta y will also get closer and closer in value, right? So if I think about the y value at an x coordinate on my pink line and my blue graph, those are going to get closer and closer together as that second x value gets closer and closer to that first x value, right? So if delta x becomes really small, then dy becomes a good representation of delta y. Okay, so we're going to use this formula to go through an example here. So compare the values of delta y and dy for this function y equals x cubed plus x squared minus 2x plus 1, and x changes from 2 to 2.05 and from 2 to 2.01. So here's the idea. Delta y is simply just the change in y value. So if I'm looking at this one, I'm going from an x value of 2 to 2.05. Delta y is simply going to be, and I'm going to call this function f of x. But delta y is simply going to be f of 2.05, the y value at 2.05, minus the y value at 2. Right? That actually gives me my change in y. Okay? So if I have I have my function here graphed, f of x is this. If I want to know what f of 2.05 minus f of 2 is, I can just plug that in here to Desmos, and that gives me this 0.717625. So that difference, my delta y, is 0.717625. Okay, I want to compare that with dy. So dy, it says in our function here, or our definition of what dy is, it's f prime of x times dx. So I want to find f prime of x times my change in x. So I need to have the derivative of this, so that should be pretty easy to do. So I'm going to take the derivative, which would be 3x squared plus 2x minus 2. I have that times my change in x. Now, what I'm concerned about is what is happening at 2. Right? That's my initial x value. That's my initial point of concern. So we are going to plug in 2 into this. And then our dx is our change in x. So what is the change in x here? It's 0.05. Right? 0.05 is my change in x to go from 2 to 2.05. So I can evaluate that, and the idea is because 2 and 2.05 are close, I should get a value for this that is close to that value. So I'm actually going to go to Desmos again here, and what I'm evaluating here is f prime of 2 times 0.05, and that gives me 0.7. You could work through that and find that same value there, but it's 0.7, so this is very close to that value. I could do the same thing. So the second one says, well, now let's, instead of going from 2 to 2.05, let's go from 2 to 2.01. Right? But I would still do the same thing. I would find what delta y is, and I would find what dy is. So I would do f of 2.01 minus f of 2. So that actual dy, that change in y value, is 0.140701. If I find my differential, f prime of 2 times 0.01, that gives me 0.14. Again, a very close approximation here to what the actual change in y is.